Hello everyone, myself Sumit Patel. Today I'm going to present one of the most important topic in the geotechnical engineering, that is the consolidation of a soil. So let us understand the concept, theories, and application of the phenomena of a consolidation in the geotechnical engineering. So first part is the introduction of a soil consolidation. In this part, we are going to understand what actually consolidation is and what are its overview and what is the actually consolidation is we are going to consider here. First is the definition of a consolidation. So soil consolidation refers to the process where soil decreases its volume over time. The decrease in the volume is because of the two phenomena we know by removing of the air voids and by removing of the water. So in the consolidation process, we are considering the removal of a water from its pore. So every soil has moisture content in it, and when we are starting the process of the consolidation, we are going to remove the water from that soil by applying the effective stresses. This phenomena is essential for understanding soil behavior under loads. So when loads are applied or building are constructed, so they enforce or they create a load on the soil, and because of that when soil get compressed, because of that compression or the effective stress applied on the soil, the water from it start to get out, or water from it get start release from the whenever the way it get, and from that the consolidation happens. So it is important to study of the consolidation property of that soil before starting the actual construction. So this is important. Importance in geotechnical engineer. So consolidation is a vital in the geotechnical engineering as it affects the stability and strength of the structure, such as the foundations, retaining walls, and tunnels. Failure to account for consolidation can lead to excessive settlements and structural damage. Highlights the necessity of accurate presentation model. So accurate prediction model before the any building is start to construct. We are going to predict how much amount of consolidation is going to happen, and because of that, how much settlement will be there. If there is a settlement beyond the limit, we have to consolidate it soil before the construction, so it can stop the whatever the further uh, whatever the further problems that are getting created in the construction sites or buildings. So next is overview of a consolidation process. Consolidation process involves the stages of primary consolidation and secondary consolidation. So they have actually three types: preliminary consolidation, primary consolidation, and secondary consolidation. So considering the preliminary consolidation as it as the load is applied, that is we are going to apply the static loads. Air voids first to get out. The first process is getting out the air void. So it is the preliminary consolidation. So 2 to 5% of consolidation will be happen there. The next is the primary consolidation, and it whatever we are denoting the word consolidation, it's actually the primary consolidation. After the preliminary consolidation or removal of air voids, primary consolidation happens where the water content from the soil start to drain out. It is the main core consolidation process where 90% of the consolidation will be happens. And next is the secondary consolidation. As in the secondary consolidation, whatever the it is the lifelong process, whatever the pores or water remaining in the pores is going to consolidate after time by time. So it is the next stage and lifeline process. So this is the next part where we are going to understand the theoretical framework. So first is the one-dimensional consolidation theory. So here is the curve. We can see the curve where the we have the virgin compression curve and recompression. So understanding this curve, we can state that from A to B here on the curve, from A to B, when the effective load is first applied, soil get compressed. Because of that compression, or effective increase in the effective, the void ratio that present will be start to decrease. And because of that load, where we can see that in the initial step compression of the soil beyond its pre-consolidation phase reflects a significant void ratio, reduce its increased effective stress. So first there is a decrease in the volume due to applied effective stresses from A to B. When those stresses are removed, as those stresses get removed there, we can again the soil get to expand to the sum of a limit, not beyond some limit, but still some limit, and it is shown by BC. It is a recompression curve. After recompression curve, again we apply load, again soil get compressed, and we can see that from B it is continued. From point D, it is a continued downward. It is because of again load applied. When we again take out the load or pressure from there, it soil gets again recompressed, or again expansion can be seen, but the expansion is not similar as the previous expansion. Those can be seen in one-dimensional consolidation theory. So, a recompression curve depicts the elastic rebound of the over-consolidated soil. So, elastically rebound that soil the soil get again it's increase its volume. So, expansion can be seen in the recompression curve, and when load applied, origin compression curve first curve it is when because of the load applied the soil volume will be get decreased. So it can be understand from this graph shown here. So next is the tergizs one-dimensional consolidation theory. So tergizs theory forms the basis of a one-dimensional consolidation. So tergizs gives some assumption before application of the tergizs one-dimension theory. There are the some assumption that must be considered in consolidation process. So first is the soil is a homogeneous and fully saturated, as soil has the maximum amount of water that it can be, and soil is a homogeneous in nature. Consolidation, whatever we consider consolidation, it cannot be applied for the layered soil. We can consider this for the only one layered soil. It is a clay, sand, anywhere, any type of a soil. For the consideration calculations and consolidation, we are considering only one uh, type of a soil, that is a homogeneity. Soil and water are incompressible. It is the second assumption. Darcy's law must be valid in that soil. The soil is a laterally confined, that is, the water can be allowed to get out from only one directions, not from the all the horizontal as well as vertical direction. So it get the laterally confined from both sides. So soil water movement can be seen vertical. Excess poor water pressure drained only in the vertical. Excess poor water pressure drained only in vertical direction. So as it is a laterally confined, excess poor water pressure can be drained in only in vertical direction only. So next is the mass spring analogy. So this is the mass spring analogy. It is the one type of experimental setup where the using the spring and mass applied on the whatever the base plate provided on that spring, we can see the behavior of the soil after application of the load, as well as the water rises and the effect of the poor water pressures after applications of the certain loads. So the mass spring analogy simplifies soil consolidation by likening it to systematic of the masses and springs, where the masses represent soil layers and the spring depict to compressibility of a soil. Model help visualize low loads lead to settlement over time, emphasizing the dynamic response of a soil to applied stresses. So let's understand the normally consolidated soil. So soil is a normally consolidated, pre-consolidated, and over-consolidated. These three types of the soil are there. So let us understand the normally consolidated soil. Normal consolidation soil are those that have been subjected to pressure equal to the current effective stresses. So no more stresses before are there should be applied. So it is the actual present load, whatever we consider the present load applied on the soil. They typically exhibit the linear compressibility characters, which make the understanding the consolidation behavior essential for accurate settlement prediction and effective engineering application. So normally consolidation soil, it is the actual present condition. That soil cannot be get uh, more soil or compressed before, or load applied before, or it also not get under consolidated. So all overall conditions are at present conditions here. So it is normally consolidated. Next is under consolidated and over consolidated. So let us considering the under consolidated soil, a soil which is not fully consolidated under the existing overburden pressure is called as under consolidated soil. So it is one of the phenomena that soil cannot get fully consolidated. So whatever the load applied, but soil does not get fully consolidated, that more load should be applied for getting the fully consolidation process. So at that time, we can consider that system as the under consolidated soil. And over consolidated soil, what we can call as the pre-consolidated soil also. A soil is said to be over consolidated if it has the subjected to in the past to pressure excess than the present pressure. So in past we have applied some pressure on the soil, and that applied pressure is more than whatever pressure we are going to apply now at present. It is called as the pre-consolidated soil. The consolidation happens before because of the applied load. It is going to fail in this pre-consolidated phenomena. So let us consider the consolidation characteristics of soil. So first is the degree of consolidation. So degree of consolidation is the, we can represent it as a U, and it is a numerical term. So degree of consolidation is depicted as the U upon U. So the degree of consolidation is the ratio of amount of the consolidation That is how much settlement is going to happen of the soil at any time interval to the total consolidation. So at present, at that time, whatever the time we are considering at that time, what amount of the consolidation is happened divided by the total consolidation of the soil, how much maximum consolidation that soil can be bear or it can be happen, the ratio of that is the degree of consolidation. So there is a time factor relationship between degree of consolidation U and whatever we can say T. The degree of consolidation is the function of a time factor. So totally it is a time dependent, that is the amount of time required to getting the maximum consolidation can be considered here. So there are two types of the drainage systems. The drainage, we can say how the water from the soil get drained out. It can be single drainage or double drainage. So water flows in one direction from the bottom only. So it is the fully thickness of the is D is the fully thickness of the soil. Next is the double drainage, water flows from the both direction, from top or from where we can consider D as the half. So this is the two type of single drainage and double drainage condition we must consider during the numerical calculations. So next is the soil structure and properties. The soil structure comprise the individual particles and their arrangement impacting its mechanical properties. Key properties include porosity, density, and degree of saturation, which significantly influence the consolidation behavior and overall soil strength. So considering we can consider the one thing as the permeability. So for getting the consolidation is depend upon directly proportional to or depend upon factor of the time. So when we applied the load, whenever load applied, if permeability of that soil is more, there are large pores and water can easily get passed from that soil, or we can drain out water as much as possible. So we can consider the sand and clay. In consideration of a sand, when the load is applied, we can able to measure the consolidation factors and all whatever numerical data required as fast as because of the high porosity of that soil or high permeability of that soil. Instead of the clay, we required a lots of time for getting the clay to be consolidated. This is the some factors which get affect the consolidation process and time required for the consolidation. So next is the phase of a consolidation. Consolidation occurs in the three phase. Primary phase, initial, primary, and secondary that we have considered before. In the preliminary or initial, the voids or whatever the voids get removed in the primary consolidation process, where we can remove the whatever the water or the main core process is that, and secondary process is whatever it's going on for time to time, whatever for a long time as load applied, the consolidation process is continued. So next is the consolidation rate and time factor. So the rate of a consolidation is influenced by the factor such as permeability, compressibility, loading conditions. Additionally, the factor plays critical role in achieving full consolidation, where the initial rapid reduction in the volume transition to a gradual decrease in the settlement over time. So as whatever the requirement of a time, whatever the increase in the load factor or considering the type of the soil, considering the permeability of the soil, all these factors get affected. The actual consolidation, whatever the percentage of the consolidation as well as the time required for the consolidation get affected by the various factors. So these let us consider about the testing methods. So laboratory test for consolidation. Laboratory consolidation tests such as the oedometer test helps determine the compressibility of a soil sample under the controlled conditions. This provides the vital details on the soil behavior under loading, aids in accurate design and construction practices. So it is the one of the advanced laboratory test consideration where the test can be done or the loading should be applied on the soil, and from that we can digitally get the data about the consolidation of that soil. Next is the field test for consolidation. So field testing methods include in-situ consolidations and piezometer installations. So it is the worldwide method using to measure the real-time soil behavior under actual loading. So load can be applied and the pressure or whatever the water rises in the piezometer can be noted there. These methods provide the insights into the consolidation process and effective site specification data for engineering applications. So next is the interpreting test result. Whatever test result we are going to interpret it in. Interpreting result for consolidation test involve analyzing the coefficient of consolidation and the consolidation settlement data. Understanding these factors is crucial for developing effective soil improvement strategies and ensuring the stability in geotechnical engineering projects. So we have to uh, we have to consider about that data, and after all overall of consideration and interpretation of data, we can able to get the various numerical factors from interpretation of that data. So this is the application and implications of the consolidation process or the consolidation theory that we are going to discuss. Whatever the consolidation, what are the applications? First is the foundation settlement analysis. As we have considered before, whenever we are going to construct the building or the base of the building, we have to consider the consolidation phenomena before it and consolidation factor. If it is the beyond a certain limit, because of that, if settlement is going to occur, it causes a lot of problems, fine cracks or large cracks in the building, tilting of the building, or building get weaker, and the stresses that not required to be generated in that structure get generated due to if we does not consider the consolidation phenomena. So it is the one of the important phenomena or characteristics behavior of this. So foundational settlement analyze assess how building settles over time due to soil consolidation. It consider factors such as load distribution, soil characters, and to evaluating potential settlement issues, ensuring the structural integrity and safety in the engineering design. So it is a must required to design or consider the consolidation factors, and to get the actual data that how much time and how much amount of soil settlement will be happens due to that consolidation. So we have to analyze the foundational settlement. Next is the predicting long-term settlements. So as we consider the consolidation is a lifetime process, it is going to happen is a secondary consolidation. After the primary consolidation, 90% of consolidation happens, but remaining the 10% consolidation will be lifetime process. It will be going to happen. So long-term settlement prediction involves evaluating consolidation rates of the soil behavior, understanding the sustained loading conditions. Accurate modeling helps anticipation structural movement, essential for maintaining safety standards and informing design adjustment in geotechnical engineering. So next is the mitigation strategies. So what are the mitigation strategies that the structure cannot be get hazard due to soil settlement of the soil settlement because of the phenomenon of the consolidation. So mitigation strategies address soil consolidation impact by employing technical techniques such as the deep foundation, soil stabilization, and drainage improvement. These methods enhance soil performance and minimize the understandable settlement, ensuring long-lasting stability in the construction project. So there are lots of mitigation processes that can be applied to remove whatever the effect of the consolidation is going to be happen. And so mitigation strategies are there. Providing a well drainage condition is the one of the important thing, so that it can be and increase the if we can compress the soil or pre-consolidation can be done. It can be helpful to avoid the whatever the in future problems that are going to be generated. So this is the overall presentation about the consolidation of the soil, and from this we can conclude that the consolidation is the one of the important behavior of the soil, and we have to consider the consolidation data, consolidation phenomena, and effect of the consolidation on the building or whatever the settlement of soil going to be happen due to consolidation before the construction of the building or before the construction of the foundations, so that if the settlement or the effect of the consolidation are beyond the limit whatever we are considering, then we have to done some mitigation measures. Pre-consolidation should be there, applying drainage should be there, compression of the soil at a certain level should be there, and because of that the stability and the strength of the soil can be increased. That consolidation phenomena cannot further affect the whatever the soil, whatever the building we are going to generate. So this is the overall about the consolidation of the soil. Thank you.